springs end up being a surprisingly important uh, bit of analysis in this class. Not just because springs are fascinating in their own right, because they are. I mean, who doesn't like playing with slinkies? Uh, and also not just because we explicitly use springs in a huge variety of objects, from the shocks in our car to the little tensioners in battery components and like battery powered things. You notice there's a little spring on one side to keep the battery tensioned in there. Uh, but also, our understanding of springs ends up being a model for basically all materials. So we need to make sure that we are all clear on what we mean by spring behavior. So a few things about springs. So first, they have a length that they like to be, right? So there is an equilibrium length. And if you've ever played with a slinky, you know that you can stretch it or squeeze it, but there is some average length that it would prefer to be. And the other thing that we know from kind of playing with them is that the more you stretch, the harder they pull. All right. We can be more explicit about why this works later, but for now I want to build up a discussion of springs based on our kind of intuitive understanding. So we're going to define an equilibrium length, and we're going to define a displacement from that equilibrium length, right? And this will be the amount of stretch. So for positive values of delta x, we'll be stretching the spring, and for negative values of delta x, we'll be compressing it. And that'll lead us to say that the force, right, the force that it takes to stretch or the force that it takes to hold a spring stretched is proportional to the amount of stretch, but also there's some constant. And we do this a lot in physics. We say we know that there's a relationship between these two things. We're going to toss in a fudge factor and we're going to let the engineers figure it out. And that's exactly what we're doing here with springs. We know that more stretching means more force, and there's some, relationship coefficient here that basically it's an engineer's job to figure out what the value of that constant is. And in fact, you'll be doing a couple of labs, where you look at the force exerted by a spring and also the energy stored in a spring. And you'll be looking at how you might determine the spring constants for various springs. Not only will you be determining spring constants, but you'll be experimentally verifying, that this linear relationship is a good relationship for springs. So keep an eye out for that in your lab sections. So this relationship is frequently called Hooke's law. And it's also sometimes presented with a minus sign here. So, and that's a matter of perspective. So the way I usually think about it is the force that you have to exert on a spring to keep it at a certain stretch. Right? So in that case, you have to exert a force in the direction of the stretch. Some other people prefer the perspective, the force that the spring exerts back on you if you stretch it. and they'll include a negative sign there to indicate that the spring is pulling back in the opposite direction of what you stretched it. So if you are stretching a spring, right, if say here's the equilibrium length of a spring, and you have pulled it out to this length, right? You have to pull it in this direction to keep it stretched, but the spring itself is constantly pulling back, trying to regain its original length. All right, any questions about this? Because I think this is pretty much all I had to say about the force exerted on or by a spring. Okay. Let's move on to the energy stored in a spring then. So if we have to exert this much force in order to keep a spring stretched, in light of our discussion from last time, a natural question is, how much work did we have to do to stretch a spring out to a given length, right? What was the energy cost of stretching that spring? And conversely, how much energy is stored in a spring that we have stretched out? Well, we can apply the work energy theorem to that. So we know that that work done by a force is equal to the integral of that force dot the dot ds, and we want to integrate from some initial equilibrium length, which we'll call x0, out to some stretched length x. So the force that we have to exert at any given amount of stretch, is given by Hooke's law. It's kx. We'll call this x final. There we go. And since we're dealing with x's here, we might as well call this ds a dx. Also notice that we took this dot product down to a scalar product because the force that we're exerting on the spring is parallel to the direction in which we are stretching it. So since they're parallel, F dot ds is the same as just F ds. All right, now that we're here, this is actually a pretty easy integral to do. Integral of x dx is 1/2 x squared. So we get 1/2 kx squared evaluated at x, the initial length and the final length. And we'll end up defining rather that the amount of energy stored in a spring at its equilibrium length is 0. So it doesn't store any potential energy when you're not stretching or compressing it. So if you do stretch or compress it, though, away from its equilibrium length, then you have stored some energy in it equal to 1/2 k delta x squared. All right, any questions here? Yes, no, maybe?